Hello everybody, it is Miss Fincham and we'll be continuing Unit 1 by covering topic 4.5, which is global wind patterns. We will be learning how the basic properties of air, as well as how the rotation of Earth give us the wind patterns that we see on Earth, and how they are also responsible for the weather patterns that we see. Thank you to Jordan Speeds for the slides and note outlines to use in this class. Our objective for the day is to be able to explain environmental factors that result in atmosphere circulation. In order to do that, we need to understand three basic factors. Those are the intensity of energy from the sun, properties of air such as density, and the spinning of the Earth on its axis, which produces something known as the Coriolis effect. Our suggested science skill to practice today is explaining relationships between characteristics of environmental concepts or models that are represented visually. The first factor that determines atmospheric circulation is how air's density changes under different conditions. The first property of air related to its density is that warm air is less dense than cold air, so it rises. If you've ever been in a house with an attic in the summer, the difference in temperature between the attic and the basement is a really great example of this property. We also need to understand that warm air holds less moisture than cold air, so think about how dry and cracked your skin gets in the winter versus summer. This is because cold winter air holds less moisture. Another factor we need to understand is that as warm air rises, it cools, and that causes it to expand. Since cold air cannot hold as much moisture, the water vapor that is in warm rising air will condense into liquid, which forms precipitation in the atmosphere and then eventually falls down to Earth as rain, snow, or sleet. Finally, after air has risen, cooled, and expanded, it is spread out and then eventually it sinks back down. We can see that happen here in the diagram at 30 degrees north and south. These properties of air help us understand the diagram to the left here, which is called the Hadley cell. The Hadley cell is a cycle of air circulation between 0 and 30 degrees, and it is largely responsible for our global wind patterns on Earth. Now that we have our basic properties of air down, which is the first factor influencing atmospheric circulation, we're going to introduce the second factor, which is the energy from the sun. Because sunlight is most direct at the equator, that is going to cause air here to warm and rise, as we can see that as step 1 in the diagram. As warm air rises, it cools and expands, and because cool air holds less moisture than warm air, the water vapor has to condense into rain. If we look at step 2 in the diagram, this is why we see such an intense rain at the equator, because that warm rising air has its water vapor condense and then fall down to the Earth as rain. In step 3, the air continues to rise and cool and expand further. In step 4, this air is expanding and spreading out even further. And then in step 5, we have cool, dry air that is sinking back down to Earth, right about 30 degrees north and south. As we can see in the diagram, this is going to explain why we see this predictable pattern of deserts forming all over the Earth around 30 degrees north and south. It is because the air that is descending back down to Earth here is incredibly dry, so we get deserts. However, we are not quite done understanding the Hadley cell. If we look at the diagram, we will see that we have this arrow here that is going from 30 degrees back towards the equator. Why is air moving along our surface from 30 degrees back towards the equator? Well, we have high pressure at 30 degrees north and south due to this column of cool, dry air that is sinking back down to Earth. When a column of air is pushing down on Earth, it gives us high pressure. Meanwhile, at the equator, we have low pressure, and that is because warm air being heated from the sun is rising at the equator, and we know that air moves from areas of high to low pressure. So along the surface, we'll see this airflow from 30 degrees flowing back towards the equator, and that is because we are moving from high to low pressure. Another way to think about this, though, is we have to get back to step 1 of the cycle somehow. We need the replacement air to come in and fill this vacuum, or this gap of air left by the air that is rising at the beginning of the Hadley cell. We have covered why air rises and expands at the equator, sinks back down at 30 degrees, and then moves along our surface back towards the equator, but that is only two of the three factors that determines atmospheric circulation. The third factor is Earth's rotation. Believe it or not, if Earth were standing still rather than spinning, wind would move more or less just straight north and south. Since the Earth is rotating, though, that means that objects such as wind, or this baseball we'll talk about here in a second, are traveling through the atmosphere and are actually deflected in the opposite direction of Earth's rotation. Another way to try to understand the Coriolis effect is to imagine that you are standing at the North Pole and you are throwing a baseball straight south. You may be aiming the baseball along this line here, but because of the Earth's spin, the baseball will actually be deflected the opposite direction of the spin. Even though the ball was traveling on this trajectory, it's going to end up here to the left of where you aimed it because the ground between the Earth is spinning. Now the same thing is true of the wind between 0 and 30 degrees. Since this air at 30 degrees is moving from a high pressure system back down to a low pressure system, it would flow directly south or directly north in the southern hemisphere, but because Earth is spinning this direction, the wind from 30 to 0 is deflected the opposite direction. What we get is wind moving from east to west between 30 and 0 degrees. Now, because 30 is a higher pressure area than 60, wind is also moving from 30 degrees out to 60 degrees. The wind in this direction, though, is deflected in the opposite direction as between 30 and 0. That is because the Earth at 30 degrees is spinning so much faster than it is at higher latitudes, at 80 or even at 60 degrees, that the wind is actually going to be deflected in the same direction as Earth's spin. That is a confusing concept, so let's talk about this. Using the example of a treadmill, imagine you're running along a treadmill that's going 15 miles an hour, and suddenly you jump to a treadmill right next to you that's moving in the same direction, but it's only moving 2 miles an hour. So it's moving far more slowly. You're going to have so much momentum coming from the 15 mile an hour treadmill and then jumping over to the 2 mile an hour treadmill. It's going to cause you to run forward quite a bit. And this is why we see wind from 30 to 60 degrees actually traveling in the same direction as Earth's spin. It is because the Earth is spinning so much faster at 30 degrees than 60 degrees that the wind is deflected in that direction of the Earth's spin. So let's put together all three factors: the sun's energy, the air properties like density, and the Coriolis effect, to take a look at how Earth's global wind patterns are a result of those factors. The first thing I want to do here is point out that the Hadley cells here still works the same way. We're just looking at it from a side view where we see all of Earth rather than looking at it from the viewpoint of being on Earth's surface like we did on our first slide. If we look at the Hadley cell, we can remember that the sun's rays are striking the equator most directly, and that is heating the air here and causing it to rise. Then as it sinks back down at 30, and because of this high pressure system at 30, the air is going to be moving out towards 0 and 60. And we can see that here with our low pressure at the equator, our higher pressure at 30, and then our low pressure again at 60. So we are going to get air moving out from the 30 towards the 60 and towards the equator when we look at this Hadley cell. And remember that air does not move in a straight line. It is deflected based on the direction of Earth's spin. So between 0 and 30 degrees, we have our air moving from east to west, and we call those eastern trade winds because they used to drive trade from the east to the west, because the ships were dependent on sails. This also drives the circulation of the ocean currents in a clockwise direction in the northern hemisphere and in a counterclockwise direction in the southern hemisphere. Then remember that between 30 and 60, the wind is blowing from west over to the east, and this is because the Earth at 30 degrees is moving so much faster than out at 60 or 80 that the wind is deflected in the same direction as the Earth spins, so it moves from west to east. This means that in North America, where we live, we get our weather from the west. So if you're looking at the radar to see if we're going to have a snow day this winter, you're going to look over at St. Louis or Chicago, because you know that the storms are headed our direction because we have westerly or western prevailing winds. This means our weather moves from the western United States over to the eastern United States. Our suggested science skill for practice today is explaining relationships between characteristics of environmental concepts or models that are represented visually. I want you to see if you can explain how the sun is responsible for the pattern of air circulation that we see in cycle C on the diagram. When you have completed your notes, please take photos of them and upload them into Canvas at 4.5 Global Wind Patterns.